Hey everyone, and welcome to the AI Research Roundup. I'm your host, Alex. Today we're looking into a paper published, well, the abstract doesn't give a specific date, titled BIP3D Bridging 2D Images and 3D Perception for Embodied Intelligence. This work tackles how AI systems perceive their 3D environment, instead of just using point clouds which can have issues. BIP3D takes an image-focused approach. It uses rich information from 2D images, combining it with 3D positional data to get a better understanding of the scene for things like robotics. Okay, so Figure 1 here really helps visualize the difference between these approaches. On top, you see the traditional point-centric model. It primarily takes a point cloud, processes it with a 3D encoder, and might optionally fuse an image data later. Below that is the image-centric model, like BIP3D. This starts with the images, uses a 2D encoder, and then fuses an optional point cloud or depth map information before decoding. It's basically flipping the primary input source. Okay, so Table 1 kind of lays out the landscape of these different methods. You can see most existing ones are point-centric, like we just talked about. But BIP3D is listed with image as its main modality. It still uses point or depth data and obviously image data, but it also ticks the boxes for multi-view fusion, using text input, being single stage, and importantly, doing both detection and grounding simultaneously. This really highlights how BIP3D integrates several key features, aiming for a more comprehensive understanding from that image-first approach. So Figure 2 lays out the actual architecture for BIP3D. You can see how it takes in multiple inputs, the text instructions, the multi-view images which are central, and optionally the depth data. These get processed by encoders, then passed to a feature enhancer which combines the text and image features, and a spatial enhancer which cleverly adds the 3D spatial information. Finally, a decoder fuses information across all those views, outputting the 3D scene understanding like bounding boxes. It's built on the grounding dyno model. Okay, so we just saw the architecture. Table 4 now kind of breaks down the size of those different modules in terms of parameters, comparing BIP3D to the embodied scan grounding model. ESG, what really stands out is where the parameters are allocated. BIP3D puts way more into the 2D image encoder, about 28 megabytes compared to just 1.4 for ESG, but its 3D encoder is tiny, less than 1/10 of a megabyte compared to over 87 for ESG. This really reflects that image-centric design we talked about, leaning heavily on the 2D processing. The text encoder and decoder sizes are more comparable. Alright, so shifting from the model size comparison, let's look at how BIP3D actually performs on a specific task. Table 3 shows the results for 3D visual grounding on the embodied scan dataset. This task is about locating objects in 3D based on text descriptions. And well, BIP3D really shines here. On the validation set, it achieves an overall score of 54.66%, which is a huge jump, over 15% higher than the embodied scan baseline. It also performs really well on the test set, even beating other methods like DenseG when using a model ensemble. This really backs up the idea that focusing on those rich image features pays off for understanding and grounding objects in 3D space. Okay, so we just saw how well BIP3D does on 3D visual grounding. Table 2 now shifts the focus to the 3D detection task, again on the embodied scan validation set. This is measured using average precision, or AP3D. And again, BIP3D comes out on top. Its overall AP is 20.91%, which is more than 5.5% better than the embodied scan baseline. It's particularly strong on less common or tail categories, and also on detecting small objects. Interestingly, even the version using only RGB images. BIP3 DRGB beats the baseline that uses depth data. So, yeah, strong detection performance here too. So we saw BIP3D does really well on 3D detection. Table 6 here looks at one of the reasons why. This is an ablation study testing a technique called camera intrinsic standardization, or CIS. Basically, it tries to handle differences in camera setups by standardizing the parameters before processing. And you can see by comparing the rows with and without the CIS checkmark that using it consistently helps improve the detection scores across different evaluation sets. The paper mentions it improves the detection AP by about 0.7 to 1.3% overall, depending on the inputs used. So, yeah, this standardization step definitely contributes to the model's robustness and generalization. So yeah, little tweaks like that camera intrinsic standardization really add up, helping BIP3D achieve those impressive scores on 3D grounding and detection we saw earlier. I think the key takeaway is how effectively it leverages rich 2D image features for 3D tasks, which is really crucial for developing robots and AI systems that can understand and navigate complex real-world environments. Well, that's our roundup for this week. Thanks for listening. I'm Alex, your host for the AI Research Roundup.